In this video, I want to use some basic energy conservation ideas to derive an equation to calculate the kinetic energy of an object based on whatever velocity it has. So up until this point in class, we've talked about energy bar graphs, ways to show where energy is being stored before an event happens and after an event happens so that we can get an energy conservation equation. And we've derived some equations to figure out the amount of work done on a system, the amount of energy stored as spring potential energy for a stretched or compressed material, and the amount of energy stored as gravitational potential energy if a mass is raised to some height above zero. The only equation we don't have yet is one to calculate how much kinetic energy an object has based on its velocity. If you're curious and want to know how did we come up with our equation for the work done on a system by an outside force, or how do you think about using energy bar graphs to get an energy conservation equation, I'm going to have all of these videos linked in the description below. To derive the equation to find the kinetic energy an object has when it's moving, we're going to look at a situation where there's a system of a fan cart feeling a constant force accelerating it over some displacement d. We'll assume it starts at a velocity of 0, reaches some final velocity, and it's on a level track, so there's no change in gravitational potential energy, there's no springs involved, so there's no spring potential energy. We're going to assume friction is negligible, so there's no increase in thermal energy, so all the positive work done on the cart by the air, because the air is applying an external force to the system and the system is being displaced, it's all being stored as kinetic energy in the end. So here's what an energy bar graph would look like for that. Assuming it starts from rest, that the cart starts at a height of 0 and there's no springs, the cart system stores no energy in it at all. And in the end, once it's been displaced some distance d, it's moving, so there's going to be some energy stored in our kinetic energy account. And where did that energy come from? Well, came from the positive work done on the system by the air particles. The air particles were applying an external force to the system, pushing on it in the same direction the system was moving, and so there's positive work done. So our energy conservation equation is the work done by the air is equal to the final kinetic energy. And we have an equation for calculating the amount of work done on a system when there's an external force applied in the same direction as moving, or if the external force is parallel with the direction of displacement, it's just F times d. And in this case, the force is in the direction of the displacement, so we're just multiplying the size of the external force times the distance. And so this is an equation that would tell us the kinetic energy of this fan cart if there's positive work being done. But we want to derive an equation that says the kinetic energy of an object is equal to something based on how fast it's moving. Well, if this fan cart is feeling a constant force over, let's say, a known displacement d, we know enough physics using kinematics and Newton's second law to figure out how fast that cart should be traveling if it is displaced a certain distance d and feels a constant external force. So let's answer this question first, which will actually get us to the kinetic energy equation we want. So the question is, what is the final velocity of the cart with mass m if it feels a constant force F over a displacement d? Well, let's go back and use our third kinematic equation where we could find out the final velocity of the object if we know the initial velocity, the acceleration of the object, and the object's displacement. Well, this cart starts from rest, so the initial velocity, that term goes away. 0 squared is just 0. And x minus x sub 0, remember, is the final position minus the initial position, which is the change in position or displacement. And given the symbols that we have here, we have a displacement, we'll just say d. So we can rewrite our simplified equation as the final velocity squared that the cart reaches is just equal to 2 times its acceleration times its displacement d. If this fan cart is feeling constant force over its displacement, then it should have a constant acceleration. And remember, Newton's second law tells us that an object's acceleration will be equal to the sum of the forces it feels divided by its mass. This cart is not just feeling this one outside force, there's gravity pulling down and the normal force pushing back up, but those things will be balanced. So the sum of the forces on the cart is just F, and if we divide by the mass, that's going to be the same as the size of the acceleration. So instead of acceleration, we could just plug in the force it feels by the air divided by its mass. So now let's just do a little bit of algebraic simplification and see what happens. So I'm going to first multiply each side of this equation by m. So we're going to multiply the right side by m so it cancels, which means the left side will also be multiplied by m. So we get m times the final velocity squared is equal to 2 times the external force the system feels times the displacement of the system. Now I'm going to divide each side by 2. So the right side divided by 2 cancels it out, which means the left side will be divided by 2. And so what do we get? We get the left side is 1/2 times the mass of the object times its speed squared is equal to force times distance. The external force the system feels times its displacement, d. But what is F times d in this case? Well, F times d is the amount of work done by the air, and where's all that energy transferred into the system being stored in the end? It's being stored as kinetic energy. And so we can see that the kinetic energy of the cart is equal to 1/2 of the mass of the object times its velocity squared. And this is our general equation to calculate the kinetic energy stored by any moving object. All we have to do is multiply 1/2 times the mass times the speed squared. Now we have a full set of equations and a conceptual way to think about coming up with an energy conservation equation to solve pretty much any quantitative or symbolic energy problem you could be asked.